So we're starting into chapter 11 now. Again, we've only got a few minutes to kind of just get things started here, but it's going to be an important kind of group of concepts, and they're not unfamiliar concepts to us in terms of talking about concentration. So if we go back to where we were just a couple of weeks ago, and if it felt like we blurred through chapters 4, 5, and 6, we did it. We did those in about 3 weeks. And that is actually really normal. So it hasn't been that long since we talked about aqueous solutions in chapter 8. And when we did, we talked about concentration primarily from two different kinds of focus. We talked about molarity, that is moles per liter, and we talked about mass percent and kind of the variations of that in parts per million and parts per billion. They were all mass focused, though. I could use mass to figure out moles. I could use mass to measure out the total amount of solution. But we have to recognize that there are some issues with just looking at things from that perspective. So if we come back again to the idea of molarity, remember, molarity was moles of solute per liter of solution. It's a really useful unit. We use it all the time. Almost every solution in our laboratory is given to us using this unit because of how useful it is and because how useful that concentration is for doing things like stoichiometry. But there's a problem with it. Because we have volume here in this denominator here, we've got something to worry about. And that something to worry about is temperature dependence. We know that when temperature increases, we will see an expansion of most objects, thermal expansion. We know that when temperature decreases, we will see a contraction of some objects, thermal contraction. Now, those differences may not be that much, but they're enough that if we are fluctuating over a wide variety of temperatures, that our molarity is going to change significantly enough to notice as we go from high temperature situations to low temperature situations. And so for that reason, we can't use molarity in those situations because it's not a consistent value. So what we have to do is we have to have another way of measuring concentration that doesn't have this temperature dependent component, so that when we are doing temperature studies, we don't have to worry about the variability of these fluctuating temperatures. And that's where molality is going to come in for us. Now, on its surface, I could flip between these two, and you wouldn't notice a whole lot of difference in the calculation of the equation. We went from a capital M to a little m, and all that we really did was change this denominator. Instead of moles of solute per liter of solution, we're now looking at moles of solute per kilogram of solvent. The advantage to this is it's still a mass-based kind of calculation. If I'm making an aqueous solution, all I need to do is measure out my water on a balance before I make the solution. So because the two are very, very similar, the notation is very, very similar as well. Capital M for molarity, lowercase m for molality. But again, because we are dealing with masses here, there's no temperature dependence. Mass is an independent measurement of temperature. There's no relation between the two. And so where we find molality used are in situations where we are going to note temperature differences and temperature changes. And so, again, looking ahead to next week in lab, you're going to be doing an experiment where you mess around with the freezing point of a solution. That's a perfect application for molality because you're going to be messing around with temperature. And so you need a consistent measurement of concentration so that you can monitor that temperature change accurately. Now, because there is a relationship between the two, there is a conversion that we can do between them. And so very similarly to what we did in chapter 8, where we were able to use density to convert between molarity and mass percent, we're going to be able to use density again here to convert between molarity and molality. The only difference is that the calculation here is just slightly more complicated because we're not dealing with solution to solution, but rather solution to solvent and vice versa. So there's an additional layer of subtraction that has to go into this that wasn't in the previous one. So if you understood the conversion in chapter 8, this really isn't that much more, but there is that one additional step that does tend to make things a little bit more difficult. So let's take a look here at an example. Determine the molality of a 0.194 molar nitric acid solution if the density of that solution is 1.10 grams per milliliter. Now, the key to this kind of problem, once again, lies in knowing what our definitions are. We want to go from molarity to molality. So we want to go from 0.194 moles of nitric acid over 1 liter of solution to moles of nitric acid over kilograms of water. Now, one nice wrinkle that we have here that we didn't have in chapter 8 is that the conversion between moles of nitric acid and moles of nitric acid is 1-to-1. So whatever value is here, we can automatically just move that over into the numerator of the new fraction that we're trying to calculate. The real trick is having to convert that liters of solution into kilograms of water. What we have to do is we're going to have to turn the liters of solution into grams of solution using the density, and then subtract from that the grams of nitric acid to give us the grams of water that we can then turn into kilograms. So that's what we have to do. This is the wrinkle that is different. Because remember, all that we had to do really in the mass percent calculations, we had to turn the moles into grams, and we had to turn the liters of solution into grams of solution by applying the density. Two relatively simple conversions. Well, these are two relatively simple conversions as well, but we're either going to have to add them or subtract them to get them to work. So for the grams of solution, I have 1 liter, which is equal to 1,000 milliliters of solution. And density says that for every milliliter, I get 1.10 grams. So that is 1,100 grams of solution in total. To get the grams of nitric, I have to convert the moles of nitric. 0.194 moles of nitric acid. One mole molar mass of nitric acid, 1.01 for the hydrogen, 14.01 for the nitrogen, 3 times 16 for the oxygen, 63.02 grams. So if I multiply that by 0.194 to 3 sig figs, I get 12.2 grams. I need to subtract these values from each other. 1,100 minus 12.2. From a sig fig standpoint, this can get a little complicated. We have to remember that this number is known to 3 significant figures, so this 0 is actually significant, which means the tens place is significant. So 1,090 would be the properly rounded value here, not 1087.8 or 1088. Now, that being said, if you make that little mistake there, I'm not going to be too hard on you for it, because it's a tough one to kind of get your head around. In the grand scheme of things, it's not going to matter too much. It's not going to affect the answer too greatly. So 1,090 grams is 1.09 kilograms. So if I put that in the denominator of the fraction, 0.194 divided by 1.09, the 3 significant figures would be 0.178 molal nitric acid, HNO3. And remember again, for concentration, it's important to have all 3 components. I need to have the value rounded to the correct number of significant figures. I need to have the concentration unit, and I need to have the solute there, all 3. So I will say, this is going to take a little bit of practice and getting used to. But if you take the similar approach to what you did in Chapter 8, slide that moles across, break down the denominator into its parts, it's a lot easier to deal with than trying to do it all in a series of calculation steps. So that would be my advice to you there.